Hello dear students, welcome to the channel and welcome back to another video of this playlist. In this playlist we are discussing the basic transformation which allows our signal to move from time domain to frequency domain. And up until now, so far we have seen frequency transform, we have seen Fourier transform, we have seen Laplace transform, and also Z transform. In previous class, we saw properties of Z transform and what is a Z transform before that class. So today we are going to discuss the remaining topics. We are starting with inverse Z transform and gradually we move towards the causality and stability of my Z transform. So now talking about the inverse Z transform, there are three ways we can obtain Z transform, inverse of the Z transform. The first way will be the power series expansion. So we can use the power series in order to find the Z transform or Z inverse Z transformation of my signal. We can use partial fraction expansion in order to find the inverse Z transform, and we can use the contour integration in order to find the inverse Z transform of my signal. So first one is the inverse Z transform using power series expansion. Now we all know what is the basic formula of Z transform, right? You can see that written right here. X of z is equals to summation n equals to minus infinity to infinity x of n into z raised to minus n. And you can represent the same formula using series expansion as well, right? So it can be written as uh, x of if we take up to x of minus 2 z raised to 2, because minus 2 will be plus 2, then x of minus 1 z raised to 1, x of 0 z raised to 0, x of 1 z raised to minus 1, x of 2 z raised to minus 2, plus up to it will go till infinity. And from this expansion, the sequence of my x of n can also be written using this formula, right? Because x of n is basically going from minus infinity to infinity, so it will go till minus infinity and through minus 2, minus 1, 0, 1 and 2 till infinity. So you can obtain the power series expansion directly or by long division method, which is very basic thing, right? Remember when we used to take the in back in the calculus class, when we used to take the differentiation of polynomials. So you can use that technique and you can derive the inverse Z transform. Next way we can find the inverse Z transform for my signal will be the partial fraction expansion. Now I'm pretty sure you all have seen the partial fraction expansion in back in the calculus class or advanced advanced mathematics class. So you can perform these four steps in order to find the Z transform, inverse Z transform of your frequency domain signal. So first you have to arrange your Z transform in the given order. See, order will look like this: x of z divided by z. Numerator, in numerator you will have your polynomial, and in denominator you will have x minus p1. You will have z minus p1, z minus p2, up to z minus pn. Now what you can do about your numerators, you can separate the whole thing in step 2. In step 2, what you're going to do, you are going to take a1, a2, a3 up to an separately, and you are going to take the denominators separate: z minus p1, z minus p2, z minus p3, up to z minus pn. And when the value of ak will be equal to z minus p of k, xz divided by z, where z will be p of k, and the value of k will keep changing from 1 to up to n. And by doing that, this equation will only be satisfied, right? If ak's value is not this value, then this value will not never be equal to this value, right? so you can have the glimpse of it from that only. Now if my x of z divided by z does have the pole of multiplicity n, then what will happen? My denominator will get the power raised to n. So that's what exactly happening here. X of z by z equals to numerator polynomial divided by z minus p raised to n, right? Because we are, what are we doing here? Z minus p1, z minus p2, z minus pn. So we are going z minus p raised to n, which can also be represented using this way, using this formula, right? Now whenever the value of a1, a2 up to an are given as uh, ak equals to 1 n minus k factorial d raised to n minus k divided by d of z n minus k into z into this term where z equals to p, which means value of z and p are equal. At that time value of ak will be this, and here again value of k is moving from 1 to up to n. Now again this value, the value of a of k will be this value whenever z will be equal to p, right? And the previous equation, the first equation which we saw earlier, this equation of step 2, we can also write this equation like this: a1 into z divided by z minus p1, a2 into z divided by z minus p2, right? We are doing nothing new. This z divided by x of z is going into the multiplication of a, so there is simple trick in that. Now what you can do, you can take z common from the denominator and you can cancel out both of the z's, so you will be left with a divided by 1 minus p1 z inverse plus a2 divided by 1 minus p2 z inverse up to a n divided by 1 minus pn z inverse. Now all the terms in above steps are up from ak 1 minus pk z inverse, and these terms are depending upon ROC of my Z transform, right? So your Z transform pair must be used in two different ways, either causal or non-causal. So whenever you are using it from causal way, it will be p of k u of n, p of k raised to n into u of n. The Z transform of this signal will be 1 divided by 1 minus p of k Z inverse. Remember we discussed about the Z transform of unit step signal, right? In the previous classes we have discussed about the Z transform of unit step signal. So if you haven't checked out previous class or this playlist, you will be seeing the link in flashing in the top right hand side corner. You can click on it and you can check it out. Then you have for non-causal, you will have, if you have non-causal sequence, then minus pk raised to n u of minus n minus 1. The Z transform of this term will be 1 divided by 1 minus pk Z inverse, right? So the Z transform for both of them will be equal, but the difference here will be the ROC, right? And ROC Z transform will be Z will be greater than A, and for the other term Z will be less than A. So in first one ROC will be the whole plane except for one radius or one circle, and in the second one ROC will be only the part inside of that circle. Now we have seen the Z transform using partial fraction. Now see the third method, which is called Z transform using contour method, right? Z transform using contour method, sorry, inverse Z transform using contour method. So earlier in first two methods we are using a lot of mathematics, so expect a lot of mathematics from this point, right? From this point on you have to expect so much mathematics, because we have discussed LTI system, we have discussed all type of mathematical transforms, so you must be habitat of that till now. So we can obtain the inverse Z transform of my signal using this contour integration in 3 steps as well. And for that we are going to take help of Cauchy integral theorem. uh, I hope you do remember what is Cauchy integral theorem. You must have studied in the calculus class. So we are going to use that Cauchy integral theorem. So first what you have to do, you have to define the function x0 of z, because we have to find the inverse Z transform. So initially you will have Z transform value, and uh, you have to expand the denominator into the product of number of poles. How? So this way, x of z will be x of z into z raised to n minus 1, and this equation you can also write it this way, equals to n of z divided by pi I equal to 1 to m z minus pi of pi raised to m, and m will be the order of my pole, right? It will be the order of my pole. Then the next step will be, for simple poles, what we are going to do, we have do two different kind of poles, simple and complex poles, right? So for simple poles, we are going to take m equals to 1, and the residue of x0 of z at pole pi can be given using this formula. Res x0 of z will be equal to limit z tends to pi z minus pi into x0 of z. So this is the second step, and if you are having multiple poles of order m0, then you can calculate the residue of x0z using this formula. The formula will completely change, so it will be equal to 1 divided by m minus 1 factorial d raised to m minus 1 divided by dz d by dz m minus 1. So you are taking degree of integral into z minus pi raised to m x0 of z, where z will be equal to pi. And if your x0 of z is having simple pole at origin, then your n will be 0, right? And you will be able to calculate x of 0 independently. And in the next step, we will be simpling using residue theorem, and we are going to calculate the x of n for poles inside the unit circle. So now that we have determined where our poles will be, definitely in the unit circle. So based on residue theorem, you can find out the x of n, and it will be equal to summation of I equals to 1 to n residual of x0 z from z equals to pi. And for the poles outside the counter of integration, you can give the equation of them using same formula, but the formula will have negative sign, as all the poles are laying outside the contour of region. So this method is little bit complex because it is based on the type of pole you are having, but you can also use either of these methods in order to obtain your Z transform, inverse Z transform. Now next thing we are going to talk about will be unilateral Z transform. Sometimes it is also called one-sided Z transform as well. So if you see instead of unilateral one-sided Z transform, then you can also understand it in terms of unilateral Z transform, which is always defined for causal sequences, which means the value of n will always be greater than or equal to 0, right? Because n equals to -1 -2 will not exist, right? So it will always be defined for n greater than or equal to 0, which means only for causal sequences. And because it is getting defined for n greater than or equal to 0, we will have some modification in the formulation of Z transform. It will look something like this: x of z equals to summation n equals to 0 to infinity x of n z raised to minus n, right? So see, the modification is taking place here in the term of limit of summation. Previously it was minus infinity, but we are not considering the points from minus infinity to 0. We are, because this is a causal signal, so we will be considering the points from 0 to infinity only, right? And this unilateral Z transform can be solved using difference equations with initial conditions. which we saw something similar for Laplace as well, right? So you can obtain the inverse Z transform using any of the methods we discussed here. And in case of all sequence, in case of the unilateral Z transform, all sequence will be causal. And one more thing, that unilateral and bilateral Z transform are same for causal signals. So if your signal is causal, which means the bilateral Z transform of my signal will be same as the unilateral Z transform of my signal, but it will not be true for my non-causal signals, right? If my non-causal signal, uh, if I'm having a non-causal signal, then I will be able to find the bilateral Z transform of it, but I will not be able to find unilateral Z transform, because it I will not be able to find unilateral Z transform, because unilateral Z transform can only be defined for causal sequences. Now let's see a couple of properties of Z transform. We're basically going to see two different properties of my Z transform. First is going to be time shifting. So what does time shift property has to tell us? It tells us that for x of n, if I'm having a signal x of n, if I take Z transform of this x of n, so it will be x of z. And then remember we discussed power series earlier. So if I'm having x of n minus k, so time shift property says if I take the Z transform of this signal x of n minus k, the Z transform of that signal will be equal to x of minus k plus x of minus k plus 1 z inverse plus up to x of minus 1 z raised to k minus k plus 1 plus x raised to minus k x of z, right? It will go that further, and let's try to prove it. Let's see how it will take place. So first let's consider my signal y of n equals to x of n minus 1, and then let's try to find out the Z transform of this function. So you all know what is the formula for Z transform. It is y of n into z raised to minus n. So the formula will be summation n equals to 0 to infinity x of n minus 1 z raised to minus n. Now what you can do, because this signal is going from 0 to infinity, we can take the value of x of 0 separately, right? If I put value of n equals to 0 in this formula, what I will have? X of minus 1 z raised to 0. What is the value of z raised to 0? Z raised to 0 is always 1, right? So only thing I will have will be x raised to minus x of minus 1. And in this x of minus 1, I can write this x of minus 1, and I can write the rest of the term as it is. I can write summation of n equals to 1 to infinity x of n minus 1 into z raised to minus n, right? Now let's put n equals to m plus 1, or you can also write n minus 1 equals to m in this equation. So what we will do, we will keep this x of minus 1 as it is, and then we will write, instead of n equals to 1, we can write uh, instead of m plus 1, right? And so that the limit of m will be 0 to infinity, because what is m? M is n minus 1. So here limit will get changed. Instead of n minus 1, I will be writing x of m, and instead of z raised to minus n, I will be writing z raised to minus m plus 1. Instead of n, I'm writing m plus 1 here. Again, in the next term, I will keep x of minus 1 as it is, and this bracket, I'm going to break this bracket, so we can write z raised to minus m and z raised to z inverse separately. Now I can take this z inverse outside of this summation mark, and I can write it x of minus 1 plus z inverse summation of m equals to 0 to infinity x of m into z raised to minus m. And again, see, this is the formula of Z transform of x of m, right? So what we will have x of minus 1 plus z inverse x of z, right? So what did we obtain? We obtained the Z transform of x of n minus 1. And what did it came out? It came out x of minus 1 plus z inverse into x of z. Right. So if we add one more term, what will be the Z transform of it? Can you tell me? If I, instead of putting x of n minus 2 here, instead of n minus 1 here, if I use n minus 2, what will be the value? It will be x of minus 2 plus x of minus 1 into Z inverse plus x of z into z raised to minus 2, right? Based on this thing, just like the first one, right? And if this result gets generalized, then we can write the same thing for x of n plus k as well. Earlier we wrote for x of n minus k. So we can, instead of this, we can also write for equation x of n plus k. So what will be the value of n plus k? Please write it down in the comment section below. Let's see who figures it out first, who understands it first. And whoever does it, I will be giving you shout out to that person. Let's see the next one. Next one is the final value theorem. So the final value theorem, what does it tells us? So it can be given as x of infinity equals to limit z tends to 1 minus z inverse into xz. And here x of z will be unilateral Z transform, definitely. Now let's try to see what will happen when we try to find out Z transform of this value infinity. So when we take k equals to 1 in time advance equation, and you can write the formula which we saw in the time shift this way. When we take plus operation, I'm not talking about earlier we took the minus operation, we can take plus operation as well. So when you take plus operation, you can write it this way: x of n plus 1, you can, when you take the Z transform of x of n plus 1, it will be minus x of 0 into z plus x of z into z. Now you have to find the Z transform of this value. So when you want to find the Z transform, what will you do? You will simply implement the Z transform formula. So you will be writing summation n equals to 0 to infinity x of n plus 1 z raised to minus n. The other side will remain as it is, minus x of 0 into z plus x of z into z. Now what you are going to do, interesting thing, you are going to subtract x of z from both of the equations. So when you do so, you can write LHS this way, because x of z is common in both of the terms, right? So you can write it this way: summation n equals to 0 to infinity x of n plus 1 z raised to minus n minus summation n equals to 0 to infinity x of n z raised to minus n. Instead of this, x of z, right? Because what is the inverse Z transform of x of z? It is basically x of n. And what is the formula for x of n? It is basically this. So you can write it this way: it is basically the formula of x of n, which will be, again, obviously will be equal to x of z into x of 0 into z plus z into x of z minus x of z. Now you can take x of z common from both of these, so you can write z minus 1 into x of z. Now what you have to do, you have to take the limit at z tends to 1, and when you take the limit z tends to 1, what will happen? This x of 0 will move out, and the limit will only be implemented to this term z minus 1 into x of z, right? And when you implement that limit, what you will get? So you will get something like a point which will look something like this. See, summation n equals to 0 to infinity x of n plus 1 minus summation n equals to 0 to infinity x of n. So here we have what did we do? We took z raised to n minus 1, z raised to n minus 1 common on both of the side, and then we eliminated it. And after that, sorry, not eliminated, this will be the basically the formula of Z transform of x of n, right? So we wrote it, and this will be basically formula of Z transform of x of n plus 1. So we wrote it, sorry, we didn't eliminated anything. And we will be having minus x of 0 into z plus z minus 1 x of z, and when you take limit of it, you will get this minus x of 0 outside the limit. The term which will be inside the limit will be z minus 1 x of z. Now what you can do, you can write it this way as well, and summation n equals to 0 to infinity x of n plus 1 minus x of 0 minus summation of n equals to 1 to infinity x of n, something that we did earlier as well when we were talking about time shifting theorem or time shifting property. We did the same thing, remember? So we can do the same thing again, and you can equate it the same way. And when you equate it same way, you can cut this minus x of 0 out, both the sides, and your equation will look something like this: summation n equals to 0 to infinity x of n plus 1 minus summation n equals to 1 to infinity x of n, which will be equal to this other term, right? Now when you expand this equation on the left hand side, what you will get? You will get a term which will look like this: limit n tends to infinity x of 1 plus x of 2 plus x of 3, which will go up to x of n plus 1, and you are subtracting another term from it. See, you are subtracting another term, and that term will be x of 1 plus x of 2 plus x of 3 up to x of n. So when you do the math in both of these sequence, you will be seeing that x of 1 will be getting subtracted from x of 1. Basically everything will get cut out, and only thing which will left in the end will be x of n plus 1. So you are basically taking limit n tends to infinity x of n plus 1, which will basically be equal to x of infinity. And from that we have obtained the earlier equation we obtained earlier. X of infinity will be equals to limit z tends to 1 z minus 1 x of z. So that will be the final value theorem of your unilateral Z transform, and these were the properties of my unilateral Z transform. Now the thing which I wanted to discuss about will be the transform analysis of my LTI systems. So when we see the transform analysis of LTI system, what basically we are going to do, we will use the Z transform of we will be using Z transform of signals for the analysis of my LTI systems. And in order to do that, initially we have to understand the pole zero plots. So the system function and properties of discrete time signal, we can obtain it in the Z domain. So let's first see the pole zero plots. What are pole zero plots? So let's take a signal x of n, and the Z transform of that signal is obviously x of z. This x of z will represent the rational Z transform, right? And you can express the rational Z transform using this term. We saw this earlier as well separately, but we saw it. X of z is equals to numerator of z divided by denominator of z, and numerator will be b0 plus b1 into z inverse up to bm z raised to minus m, and denominator will go a0 plus a1 z inverse plus up to it will go an z raised to minus n. Now the poles, what are the poles? Poles are the value of z for which x of z equals to infinity, and same way zeros are the value of z for which x of z is equals to 0. Now we have already studied what is ROC. So we know that ROC is the region where x of z has finite value, which means it is the region where my Z transform converges. But poles are the location where value of x of z will be infinity, and because of that, poles will not lie in the plane of ROC of my Z transform. Same ways, zeros are the location where value of my x of z is 0. That means it will be finite. So 0 will lie in my ROC plane, right? And this equation of x of z with including numerator and denominator, now it can be represented using this formula: x of z equals to z minus z1 divided into z minus z2 up to in multiplication z minus zm, and in denominator you are going to subtract z minus poles, so z minus p1 into z minus p2 up to it will go till z minus pn. And obviously it is very clear that all the values of z1 z2, for all the values of z1 z2 up to zm, value of x of z will be 0, and value of x of z will be uh, value of x of z will be 0 for zeros, and x of z will be equal to infinity for poles. So now we are done with poles and zeros concept. Now come to the causality and stability of the system. So for causality, we all studied causality. We all saw what is a causality and how we can obtain it, what is the condition for a signal to uh, be a causal signal. So if you haven't attended that lecture, so we discussed it in the very first chapter in the beginning itself. So please check that out, please check that video out, so that you can get the hold of causal signals and causality of signals. uh, and earlier also in Fourier transform also we discussed about the causality of my Fourier transform. So if you have seen all these videos, then you will get better idea of it. But for now, let's see the causality and stability of my Z transform signal. So what is the condition for my Z transform signal to be a causal signal? So the condition of LTI system to be causal is given using this formula: h of n is equals to 0 for all the values of n less than 0. So remember earlier also when we discussed about causality, we were seeing the same formula. So for all values which are not positive values, all the values which are negative values, for all those values, value of h of n will be 0. And remember when we discussed the causality as well, we were talking about the same point. And what is h of n here? H of n is the unit sample response of my LTI system. When my sequence is causal, then the ROC will be the exterior of the circle. And that's what we saw in most of the cases as well, right? So we discussed it and we derived that whenever my signal is causal, the ROC is the exterior part of the circle. And when my signal is non-causal, then the ROC will be inner part of the circle. Then they've given the condition that LTI system is a causal if and only if the ROC of the system function is exterior of the circle of radius, which means radius must be less than infinity. And for this condition, uh, causality of LTI system can be derived in terms of Z transform as well. Now let's see another property, the stability property, right? So what the stability property tells us? So remember we discussed about the stability property earlier as well when we discussed about the stability of Fourier transform, and even before that when we discussed about the properties of system itself. So back then we saw what is the stability and how we can obtain the stability of Z transform. So we are not the stability of not Z transform, but the stability of my uh, Fourier transform. So if you remember that, we are going to do similar thing here for causality or stability. So what is the necessary condition for a system to be a stable system. Remember, we talked about the BIBO condition, bounded input bounded output condition. So if my system is BIBO system, then it will be definitely a stable system. And what was the formula, or what was the condition for my signal to be a BIBO stable system? So it was n equals to minus infinity to infinity, h of n must be less than infinity. Now let's try to see what will happen when we try to use the Z transform here. So let's take a signal h of n, and its Z transform can be given as a h of z, which will be equal to n equals to minus in summation n equals to minus infinity to infinity h of n into z raised to minus n. Now let's see, let's take the magnitude or the mode on both the sides. And after taking mode, what we can do, you can take calculate the magnitude of overall sum, and it will always be less than the sum of the magnitude of individual terms. We explained it in the Fourier transform video as well. So it will be always be less than the sum of the magnitude of the individual terms. So you can represent it this way, as h of z less than summation n equals to minus infinity to infinity h of n z raised to minus n. So here, if h of z is evaluated on the unit circle, then z raised to minus n will be equals to z will be equal to 1. And because of that, my equation will look something like this, because that term became 1. So h of z will be less than summation n equals to minus infinity to infinity h of n. Now remember, what was the condition for my system to be a BIBO stable system? If the system is a BIBO stable system, then summation n equals to minus infinity to infinity h of n will be less than infinity. And that condition will imply that my h of z is less than summation n equals to minus infinity to infinity h of n less than infinity, which means it is evaluated on a unit circle itself. So this equation is giving the stability condition in terms of Z transform to me. And also this condition will require the unit circle to be present in the ROC of h of z, right? So that we can say that an LTI system is a BIBO stable system if and only if the ROC of the system function includes the unit circle, right? If ROC of the system function will include the unit circle, then only my system will be a stable system. Now what will be the condition for my signal to be causal and stable signal, right? Both signals at the same time. So we know this condition for a causal system, we know the condition for the stable system. Now what do we have to do? We just have to combine them. So for the causal LTI system, we know that ROC of the system function h of z is the exterior circle, right? Exterior of some circle of radius r. So z here will be greater than r. And we also saw for stable system, right? For stable LTI system, the ROC of h of z must include the unit circle, which means r will be less than 1. So both of these conditions, what do they indicate? That indicates that the value of my Z transform should be greater than r, but this r should less than be equal to 1, less than equal to 1. So causal and stable system must have a system function which converges for z greater than r less than 1 for my signal to be a for my system to be a causal and stable system, both at the same time, right? So ROC of h of z does not contain any poles, and because ROC of causal and stable LTI system includes a unit circle, so we can state that all the poles of h of z of such system are inside my unit circle. So all the poles will be inside your unit circle. So now we have seen the causality and stability of the system. Let's see the inverse Z transform numerical problems. We saw two different numerical problems we are going to see today and now. And see, this one is the first of them. So we have been asked to find the Z transform of x of z using the partial fraction expansion approach. We already seen the partial fraction expansion approach in this lecture only. So we have given x of z is equals to z plus 1 divided by 3z 3z square minus 4z plus 1, and the ROC is z greater than 1. And now that you have seen what is the ROC, you must have already some idea about if my signal will be stable or if this will be causal or not. Now we know the formula, right? What did we do in the uh, partial expansion for partial fraction expansion of my z inverse? We took formula which look like this, right? X of z divided by z on uh, on the numerator we took numerator polynomial, and in denominator we took poles of the denominator polynomial. So we will need poles of this denominator polynomial, and when you find the poles of the denominator polynomial, you will find the poles will look like this: 3z, because z is common in all three of them, so z will definitely be the pole, and this 3 will come out whenever you find the poles of this equation. So poles will be z minus 1 and the other pole will be z minus 1 by 3, which means z equals to 1 and z equals to 1 by 3, and z equals to 0. So you will have 3z here. Now when you do the same operation which we did earlier when we were deriving the partial fraction expansion, what we will get? We will get equation which looks something like this: 1 by z minus 2 divided by z minus 1 by 3 plus 1 divided by z. And when you try to find out the inverse z transform of this equations, so inverse z transform of 1 by z will be 1, uh, or you can rewrite this equations using uh, by taking z common, right, or sending z into the inverse or dividing it by z. So what you will get? You will get 1, then minus 2 divided by, what you will do, you divided this whole equation by z, so you will get z divided by z, which will equal to 1 minus 1 by 3z. And if my z is denominator, if I want to send it into the numerator, what I have to do? I have to take the inverse. So 1 divided by 3 z inverse plus 1 divided by, again z divided by z, it will be 1 minus 1 divided by z, which will be equals to z inverse. So we are having z inverse, right? And from this equation we can see that poles are z equals to 0, z equals to 1 by 3 and z equals to 1. We talked about it earlier. The ROC of my signal will be z greater than 1, which will be exterior to poles as we saw earlier, and hence the time domain sequence will be a causal signal. Taking inverse z transform of equation, taking inverse z transform of this equation, what we will get? We will get my x of n is equals to delta of n. Basically this is the formula of z transform of delta. If you remember, we discussed it into the earlier lecture. What is the z transform of my delta signal in the very first lecture of z transform itself. Then we derived we saw the different properties of z transform, and based on that we saw that this will be the equation for the z transform of minus 2, because minus 2 is into multiplication, 1 by 3 raised to n u of n. From the scaling property you can derive this, and this is basically the equation of the z transform of unit step signal. We saw it in the very first z transform video. So this will be your base signal. Let's see another example of it. Now we have been asked to find the unilateral z transform of these signals: x of n equals to a raised to n u of n, and the other signal is x of n equals to a raised to n plus 1 u of n plus 1. Now unilateral and bilateral z transform are same for causal signal, remember, and both of these signals are causal signal. How do I know both of these signals are causal signal? See here, which signal is this? This is a unit step signal, and unit step signal always go from 0 to infinity. And what do you call a signal which goes from 0 to infinity? A causal signal, right? So this will be a causal signal u of n, and based on that you can say the z transform for unilateral z transform and bilateral z transform for my x of n, this signal will be same as the z transform of bilateral z transform, right? And we all know what is the based on property, you can write a raised to n into u of n. Z transform of this term will be equal to 1 divided by 1 minus a into z inverse. So let's see the next problem. Maybe it would be difficult than this. So next term asks us what is the z transform of x of n equals to a raised to n plus 1 u of n plus 1. Now see, we again know that when we take u of n plus 1, that means we have to find the z transform, right? So x of z will be equal to summation n equals to 0 to infinity a raised to n plus 1 u of n minus 1 n plus 1, which is basically my signal, into z raised to z raised to minus n. So basically we are writing the equation of z transform here. Now we know that u of n plus 1 will be 1 for all the values of n greater or equal to minus 1. So here what we have to do, we can use our brains here. We can calculate for n plus 1, we can calculate of u of n plus 1 equal to 1 for n greater or equal to n minus 1. So we can take one signal and then we can take the other signals, so that we can make it easy. Or we can do something like this. We can take summation n equals to 0 to infinity a raised to n plus 1 into z raised to minus n, because value of u of n plus 1 for all the values of 0 to infinity will always be 1. And this n equals to minus 1 we don't have to consider, because you are looking for the unilateral z transform, so you will not be considering this value, so this value will be 1. Now this term a raised to n plus 1, in this term a into you can divide this term like this, a into a raised to n. So you can take this a out because it is a constant, and the remaining term will remain into the summation. So it will look something like this: summation n equals to 0 to infinity a raised to n into z raised to minus n. Now this basically looks like a property which we saw earlier, right? And based on that we can write 1 divided by 1 minus a z inverse, scaling property. So my final answer will be a divided by, because a was in multiplication of it, so z transform of my x of n will be a divided by 1 minus a by z, or a divided by 1 minus a z inverse. So that was your numerical problems related to z transform. So this is the wrap for the z transform and this playlist as well. Next time we are going to start a new playlist, and I will be seeing you soon. Until now, thank you. Until then, thank you very much for listening. Take care of yourselves, and goodbye from me for now.